Hi folks, Chris McClure here. We're going to now have a discussion on exponential functions. And you will soon see when we get into the next section why we've had a discussion of inverse functions. Even though we talked about inverse functions in section 6.2, we will not explicitly talk about inverse functions this section. But when we get into section 6.4, which I imagine I'll record that lecture tomorrow on Friday, we'll talk about how the logarithms and exponentials are inverses of each other. So we're going to focus on exponentials this section here in 6.3. So we'll talk about exponential functions. Now, what we're talking about exponential functions is taking a number, not a variable, but a number, raised to a power. Well, we already know how to raise a number to irrational power. Like, for example, 1.4, okay, that is a rational number. You could just take 2 raised to that on your calculator just by using this button or this button. And in fact, you can raise 2 to these sequence of rational numbers. And as you pass to the limit, that exponent will become the square root of 2. So you could take 2 raised to any real number, whether that exponent is pi or square root of 2 or any other real number, positive or negative. Okay, so that's what we're talking about for an exponential function, is where you have a constant number raised to some generic power. So let's go ahead. So I encourage you on your own to go ahead and take 2 raised to this sequence of rational numbers, and then see what you get when you take 2 raised to the square root of 2. You so that you've actually taken a limit for the exponents. Now, so what we have here is a list of properties of the exponential function. Now, a is going to be a base of exponentiation, and s, t are those two are going to be exponents, where those exponents could either be numbers or variables. And remember, variables are nothing more than just numbers whose value don't you really know. Well, we're going to assume that we know that a is a fixed number. All right, so first of all, if you have these product of 2 exponential expressions here with the same base, that'll be the same thing as that same base of exponentiation with the sum of those 2 powers. And here we've got this multiplication principle here that basically says that if you have this exponential expression raised to a power, then that really amounts to just multiplying the exponents together. Here, this says that you've got the product of 2 numbers raised to the same power. Well, then you can decide to exponentiate first and then multiply. So if you want to multiply and then exponentiate, that's the same thing as exponentiating first and then multiplying. Down here, we're saying that 1 raised to any power is 1, as long as that power is not 0. And by the way, all these exponents here we're assuming are greater than 0. So that would exclude s being 0 in this case. So 1 raised to any positive exponent is equal to 1. In fact, 1 raised to any non-zero exponent is going to be 1. A raised to the negative s power is the same thing as 1 over s, or 1 over a to the s power. Same thing as 1 over a raised to the s power. And this last one says that any number raised to the 0 power is 1, as long as a is not 0. But again, remember, a, s, and t are all greater than or equal to 0, or actually greater than 0. Okay, so, all right. So one of the things that you need to know about exponential functions is this ideal of doubling. The value of the function doubles with regularity. So, for example, look at this table right here. We start off at time 0 when x is equal to 0, and suppose that our function is 5 as our starting value. Now, as you go from 0 to 1 for x, the value of the function goes from 5 to 10. All right, it doubles. But look what happens now as you go from 1 to 2 for x. Well, the function goes from 10 to 20, and then to 40, and then to 80. So each time that x ticks up a value, the function doubles. This just kind of shows that for exponential functions in general is that they have the same doubling time. So the time, meaning the value of x, that it takes to go from one value to its double is going to be the same time it takes to go to double again, and then to double again, and so forth. So, and it turns out that if you start off at 5, think about 5 as 5 times 2 to the 0 power. And then 10 is, this 10 right here is 5 times 2 to the 1 power, and then 5 times 2 to the second power would be 20, and so forth. So each time you're multiplying by 2, which increases the exponent on the 2. And so imagine that f of x is equal to the function 5 times 2 to the x power. And it works out that that is going to be double of what it was when x was 1 unit smaller for this particular case here. And actually, if you were to if you were to take this equation right here, divide both sides by the f of x minus 1, then you'll have f of x over f of x minus 1 is equal to 2. And that means that for this particular function, and every exponential function is going to have a similar property, is that the ratio of a functional value to its previous value is always going to be the same, regardless of which two consecutive values that you have. So notice that 80 over 40 is 2, 40 over 20 is 2, 20 over 10 is 2, 10 over 5 is 2. You don't get that with any other function except for exponential functions. Now, every exponential function that's in existence is going to be in this form where you have some starting value c. We know it's a starting value c because when x is equal to 0, you have a to the 0 power, which is 1, so c to the 1 is just c. So f of 0 would be c. That's why c, this constant right here, is your starting value. And to evaluate this function, would take whatever x value that you have and use that as the exponent. Now we're assuming that a is positive, but in a lot of cases we can talk about negative values for x as well. The domain of f is the set of all real numbers. Actually, a is the base of exponentiation, and we don't want it to be 0, and we don't want a to be negative. So, but the exponent could be negative or positive or even 0. So the domain is the set of all real numbers. The base a is the growth factor, so a has to be positive. It could be a fraction, smaller than 1. It could be 1, it could be greater than 1. But a is the growth factor. And c is our initial value. And here we're just reiterating what I just mentioned earlier, is the ratio of the function at one value to the value of the function 1 unit prior is always going to be the same. So we go through and choose which one of these three represents an exponential function. All you need to do is just take ratios of consecutive functional values, provided that these x values are all in a row. So for this first one here, take 5 divided by 2, which is negative, or I'm sorry, you take the slope, I should say. So and well, anyway, you take 2 divided by 5, you get 2/5. Negative 1 over 2, you get negative 1/2. 4 divided by negative 1 is 4, and so forth. And because these ratios are not the same, this couldn't be an exponential. But this could be a line. Remember, for a linear function, these average rates of change are always going to be the same. So, hey, this is going to represent the line, but not an exponential function. An exponential function would have all these ratios being the same, just like you would see here. For this second one, these ratios are the same. So this second one right here, it represents an exponential function. And notice that that average rate of change is increasing as we go with increasing values for x. Okay. So we would have 1/2 as that ratio of consecutive outputs. So this is an exponential function. And what about this function here? Well, these average rates of change are, well, they're variable, increasing with time, and those ratios are not the same as well. So this function is neither linear nor exponential. How do you graph exponential functions? Well, let's take a look at the function 2 to the x power. So you can let x be some different values, and then take 2 raised to each of those different values. And so you got a bunch of ordered pairs, and you could plot those ordered pairs like you see here. And then draw a nice smooth curve. And this is basically the shape that you'll see of all exponential functions. Notice that it goes through 0, 1. And when x is equal to 1, y is 2. No surprise, because 2 to the 1 power is 2. And also when x is negative 1, you get y equals 1/2, which shouldn't be a surprise, because 2 to the negative 1 power is 1/2. This graph is from an example in the textbook, which you could read on your own. This basically shows exponential growth in phone subscribers over the last, almost 20-something years. 3 years prior to 2009, I guess. By the way, you have y equals 3 to the x, y equals 6 to the x, and because of the fact that this blue curve is growing more quickly than y equals 3 to the x, this should suggest to you that exponential functions with larger bases are going to grow more quickly than exponential functions with smaller bases. Okay. All right, so, and by the way, if you were to compare these two exponential functions, 10 to the x versus 100 to the x, well, your 100 to the x is going to grow much more quickly than the 10 to the x function. But you go ahead and plot those in your graphing calculator. All right, move along here. Some properties of your exponential function for all positive and greater than 1 values of a. Here the base of exponentiation is greater than 1. The domain is the set of all real numbers. The range is the set of positive real numbers. So shouldn't be a surprise. You can let x be equal to any real number, but the outputs will include all positive values, all positive numbers. Never 0, never negative. There are no x-intercepts. The x-axis will be the horizontal asymptote. The y-intercept is always going to be 1 if you have this sort of function. If you have c times a to the x, then c would be the y-intercept. This function is an increasing function provided that a is greater than 1. Okay. And also this function is a one-to-one function. That means it's invertible. And tomorrow's discussion will talk about how the logarithm is the inverse of the exponential function. I could always tell you 3 points off the top of my head that lie on the graph of the equation y equals a to the x power. And it's these 3 numbers here. Per our discussion about 2 minutes ago. And lastly, the graph of this function is always smooth and continuous. No corners, no gaps, no jumps, no holes. Now, here we've got another exponential function, but this time the base is a number that's less than 1. And notice that as x increases in value, that the function decreases in value, which should not be a surprise. When you take a number that's smaller than 1 and raise it to increasingly larger and larger exponents, the function is going to become smaller and smaller, closer to 0. And indeed, here is the graph of the exponential function with the base being smaller than 1. Which, by the way, you could write this as 2 to the negative x, by the way. So compare the graphs of 2 to the x and 1/2 raised to the x power, which is the same thing as 2 to the negative x power. What do you notice about these two graphs? Well, you'll notice that they're kind of like mirror images of each other. And by the way, remember when we were talking about transforming graphs, if you replace x by negative x, that will reflect the graph about the y-axis. So no surprise that the graph of y equals 2 to the negative x, which is the same as 1/2 raised to the x power, is going to be the mirror image of y equals 2 to the x graph. So on your own, I encourage you to plot the graph of 1/3 raised to the x. Actually, let's do that together. Let me pull out my graphing calculator. Here's my graphing calculator. Let me show you how to graph any exponential function. Here we'll do 1/3 raised to the x power. Here's 1/3 and then raised to the x power. Okay? And there you can see, oops, you can see the graph of it right there. Let's go ahead and set our window. So maybe we go from, say, -4 to maybe +6 or something by 1s. Y minimum maybe -1, even though the functions will never be negative. And y maximum, call that, I don't know, 20 or something. Maybe we can make the y scale 3. And let's go back up to x minimum. I changed my mind. I want to make that -5 and x max +5. And let's go ahead and graph And notice that the graph crosses at the line, or at the point 0, 1. Because remember, any number raised to the 0 power is always 1. And I can guarantee you that at -1, that the value of the function is going to be 3. Because 1/3 raised to the -1 power is 3. And I could also tell you that when x equals 1, the function's value is equal to 1/3. And when x equals 2, the function's value is 1/9, and 1/27, and 1/81, and so forth. Take a look at and compare the graphs of these two functions here. Y equals 1 to the 6th raised to the x power. Compare that to y equals 1/3 raised to the x power. And notice that as x becomes large, that the function with the smaller base will dive down and get closer to 0 more quickly compared to the exponential function with the larger base. All right, hey folks, I'm gonna we're going to pause real quick. All right, well, I'm back with you. I had to talk with some students. So moving along here, here's properties of the exponential function when the base is some positive number that's less than 1. So just like for the other exponential, the domain is a set of all real numbers, and the range is a set of all positive real numbers. No x-intercepts, y-intercept is 1. Horizontal asymptote is still the x-axis as x goes to infinity. This is going to be a decreasing function for all values of x. Oops. And of course, the graph will contain these 3 numbers, and the graph is smooth and continuous, no jumps or holes or anything in the graph. Let's go ahead and talk about graphing exponential functions. Suppose that you have this function to graph. How would you graph it? Well, my guidance to you would be to graph the function 2 to the x, and then use the ideal of transformation to replace x by -x and add the -3. And remember what doing those things to the function will do to the graph of 2 to the x. So we'll start off with the graph of 2 to the x, and then replace x by -x, reflects the graph about the y-axis, and then subtracting 3 from the function will move the graph 3 units downward. So here's the graph of y equals 2 to the -x minus 3. Now, there are lots of exponential functions. In fact, the base of exponentiation can be any positive number. But there is a very special base of exponentiation. Besides the 2 and the 10, there's the letter e. Yes, 2 to the x is pretty common, and 10 to the x is pretty common, but e to the x is also very common. And for those of you going on to calculus, you will see your friend e here a lot. So we're going to talk about what e is. Well, imagine that you've got this sequence 1 plus 1 over n raised to the n power. And then you take the limit as n goes to infinity. Meaning you're going to let n become larger and larger. So think about n going beyond 1,000,000 and 1,000,000,000 and 1,000,000,000,000 and so forth. Well, the limiting value of this expression here works out to be some number, 2.1 1718 or something like that. It's 2.718281827 dot dot dot. So this number right here is approximately what e is as you take the limit as n goes to infinity. 2.718281827. And it's not a rational number, it's an irrational number. But look, folks, it's just a number. It just happens to be a real number that's somewhere between 2 and 3. But we always just write it as e to symbolize that limit. But just understand it as just any other number like pi or square root of 2. And hey, e to the x is a very famous and common exponential function. And it obeys all the same rules as any other exponential function. Let me go back to the graphing calculator and show you on the graphing calculator that you'll see the letter E right there indicating that you could take, let's go ahead and quit here, and you could take e raised to any power, there's e, and you want to raise that to the second power, for example, there's what e squared is. Or if you want to take e raised to the negative 1 power, there's e to the negative 1 power. In fact, you notice down here to the left, there's an e to the x button. So that'll actually bring together the e with the exponent. All you need to do is fill in the exponent. So if you want to figure out what e to the 5th power is, well, there it is. All right. And there's the graph of e to the x. It looks just like any other exponential functions graph. There's the famous 3 numbers, or 3 points on the graph. E to the 1 power is right here with 2.718 dot 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 dot, just rounded to 2.72. E to the negative 1 power is 0.37. E to the negative 2 is over here, e to the negative 3, and so forth. As x goes to negative infinity, the function approaches 0. What would be the graph of negative of e to the x minus 3? What would that look like? So look, start off with the graph of e to the x, replace x by x minus 3, and put a negative in front. In fact, if you were to just put a negative in front of e to the x, and you have the graph of negative e to the x, that would just reflect the graph about the x-axis, and then replace x by x minus 3, and that'll shift the graph 3 units to the right. Or your second step could be that you replace x by x minus 3, and that shifts the graph 3 units to the right. And then you put a negative in front of the function that reflects it about the x-axis, and you still get the same thing. So you could do those transformations in just about any order that you want. You'll end up with the same graph. Talk about solving exponential equations. Now here's kind of a hint. If you have the same base, but with these different exponents, and these two exponential equation or expressions are being set equal to each other, the only way that these two exponential expressions can be equal to each other is if the exponents are equal to each other. Okay? So if you have these two equal to each other, that means the exponents are equal. So, for example, suppose that we've got this equation here. What would x have to be? So here's what we could do. Remember that 32 is 2 to the 5th power. So now you have 2 raised to the 3x minus 1 being equal to 2 to the 5th power. That means 3x minus 1 is equal to 5. And then, of course, you can go through and solve for x. Add 1 to both sides, divide by 3. That means x equals 2. And then you can go back up here and verify that, hey, look, if you got x equals 2, 3 times 2 is 6, minus 1 is 5, and indeed 2 to the 5th power really is 32. What about this equation over here, part B? How would you solve for x there and there? Well, just use your properties of exponents to rewrite this expression on the right. Now, this e to the negative x raised to the 4th power is the same thing as e to the negative 4x. You just multiply the 4 times the negative x. And then you have 1 over 3 to the x. So you just basically are going to use properties of exponents where you subtract the exponents. Negative 4x minus 3x is negative 7x. So this whole thing on the right hand side is negative 7x. So now you have this equation of these exponentials and the bases are the same. Then all you need to do is just set the exponents equal to each other. 2x minus 1 is equal to negative 7x. And then solve for x. Maybe add 7x to both sides. Add 1 to the both sides, and then divide both sides by 9. So you conclude that x is equal to 1/9. So when x is equal to 1/9, right there, and right there, then this equation would be a true statement. We could use exponential functions in equations. In fact, here we have a function, this probability function, that says we can model the probability that there's going to be a car between 9 and 10 by saying that within t minutes of 9 p.m. that this expression right here will be equal to the probability that a car will arrive. Starting off at t equals 0 and going beyond. We're not talking about 8:55. We're talking about 9:05, for example, when we say that a car will arrive within 5 minutes. So this is an example of what we call a Poisson distribution. But anyway, so all we need to know with this function is know how to evaluate it. What would be the probability that a car will arrive within 5 minutes? Well, just replace t by 5. And indeed, 5 times negative 0.2 is going to be negative 1, and 1 minus e to the negative 1 power works out to be 0.63212. So there's about a 63% chance that a car will show up between 9 and 9:05. What is the probability that a car will arrive within 30 minutes of 9? As in between 9 and 9:30. Well, replace t by 30 and evaluate the function. And what that looks like is you take 30 times 0.2 and take the negative of that and e raised to the negative of 0.2 times 30, and then 1 minus that. And that works out to be about 0.9975. So there's about a 99.75% chance that a car is going to show up at the drive-thru at Burger King between 9 and 9:30. So it's almost certain. And if you were to graph this function, let's go ahead and graph this function. Let's go ahead and clear this function out. We have 1 minus e raised to the negative 0.2. Well, we're not going to use t, but we can use x. And now let's go to our window, starting off with 0 right down here. And x max would be 60, which would be for 10 o'clock. And we could do a tick mark every 5 minutes. Now, this is the probability function. You know that the output is going to be some number between 0 and 1. So y minimum is 0, y max is 1, and we could do a scale of 0.1. Tick mark every 1 unit. So now let's go ahead and graph. And there's the graph. So that shows that between 9 o'clock and 10 o'clock that the probability of a car coming through Burger King will rise in an exponential fashion and get close to 1 after about 20 or 30 minutes. And then it only gets closer and closer to 1 the closer to 10 o'clock that you get. If you want to look at specific probabilities, then just go into your table menu. Let's go to table setup. And we could start off at 0. And then we'll leave delta table as 1. That's the increment for the x. As in, we're going to take a look at the probability on a minute per minute basis. Starting off at 9 o'clock, 9:01, 9:02, 9:03, and 9:04, and so forth. And you can look at this probability as it increases. So after 4 minutes, there's a 55% chance that a car is going to come through. By 9:05, there's a 63% chance. By 9:06, there's a close to 70% chance. By 9:07, there's about a 75% chance, and so forth. You can look at this. So let's see here. By about 12 minutes, there's about a 90% chance that there's going to be a car that drives through. What value does this function approach as t becomes unbounded, as we get closer and then beyond 10 o'clock? And the answer is 1. And that should make sense, because as t becomes larger and larger, this exponential gets close to 0. And 1 minus that will become close to 1. So let's just review our exponential functions. When the base is greater than 1, the graph goes from essentially 0 up through 0, 1 and increases toward infinity, always increasing, and so forth. And similar discussion, but in the mirror image sense for the exponential function where the base is less than 1. And we also use the fact that if we need to solve exponential equations, then we need to get the same base on both sides and then set the exponents equal to each other and solve for the unknown variable. Okay, so that's it for this section. And I will now post this and post new homework, and we'll talk with you tomorrow. Take care. Good luck.